Hello again. Tonight we're going to talk about the star Betelgeuse, or Betelgeuse, as some people pronounce it. It's Arabic. That it's actually not exploding right now, as you might have heard in some social media stuff. It's actually what is known as roiling, and we'll discuss what all that means. So, what is this, and where is it? So, Betelgeuse is a 10 million year old red supergiant star in the Milky Way galaxy. It's roughly 700 times the size of the sun and 15 times the mass, and it's roughly 500 light years from Earth. And the reason why I use, roughly on these things is it doesn't matter the precise number, because if you look at the size of it, given that it's kind of roiling around, an exact size or exact diameter would not make any sense. And given the fact that it's giving off mass, having an exact mass number wouldn't make any sense. The distance is variable based upon its growing and shrinking. So it could be, 420 light years to 600 light years. I'll just say 500. Anyway, it's located in the constellation of Orion as one of its shoulder stars. And we have both a star chart there on the left and an image with the outline of the constellation overlaid on it. And you can see that Betelgeuse is up there in the... Now, if you're Orion the Hunter, it would be your right shoulder. If you're looking at Orion the Hunter, it would be the left shoulder. If you're below the equator, it would be the bottom shoulder, because he turns the other way. Anyway, it's the red shoulder, not the sort of whitish shoulder, gray-white shoulder. It's a variable star, which means it pulses. It gets brighter and dimmer at various periods. And it is the 10th brightest star in the night sky. So it's easy to spot. Don't need a telescope. Don't even need binoculars. There it is. Based upon theory and simulation, it is believed to be nearing the end of its life. At end of life, stars that are red supergiants typically produce a supernova, which is a very bright detonation. The star will end up being a neutron star. If it's large enough, it'll become a black hole. I think this sits more of the neutron star category than black hole. The explosion is expected to leave behind what is known as a diffuse nebula. This is just like a poof of gas and dust that's left over. It's fairly thin, as opposed to when a star like our sun, a main sequence star, goes end of life. They produce what is known as a planetary nebula. They blow a giant smoke ring, basically, and that's much denser material. So what is its brightness? Well, given that it's a variable star, it cycles through dimmer and brighter. Its magnitude varies, because it's a variable star, from 0.0, which is fairly bright, to 1.6, which is 1 order of magnitude plus dimmer, but it's still naked eye visible. Anything that's at 6 or a smaller number down into the negative is going to be naked eye visible. Strangely enough, given that it's in the 1 magnitude range, this is the variable star with the widest range of brightness. It gets dimmer and brighter over a wider range of magnitudes than any other star that's a variable first magnitude star. Its cycle period, going from brightness to dim, isn't static. It's not like a fixed number, like a pulsar has a fixed number at which the beam will shoot out. This has like growing and shrinking in brightness, pulsing, and but not a pulsar. Its period varies. It can be anything from 185 days to 230 days to 420 days to 2200 days, and anywhere in between is my guess. They're not quite multiples of one another. Like the 230, when you double it, is 460, not 420. And the 230, when you halve it, is not exactly 185. And the 2200 sounds like a multiple of 420. And so its period that it goes from bright to dim to bright is not fixed. So last year, it was dimmer than its dim expectation. So it dropped below magnitude 1.6. And they were thinking, oh, good, it's about to go nova. And then it didn't. It got bright again, but it got bright to no brighter than they expected to in the current cycle. So it went from bright, you can see the curve at the bottom, although it's a gappy curve. It went from bright to dim to bright to lost data to really dim, and then it came back up to the normal maximum brightness, and then it went back down into the normal dip of dim, and then kind of faded from there. So they were trying to judge, why did it get so dim? The first thought they had was, there's some debris around the star, and it kind of blocked the light from getting to Earth, so it looks like it got dimmer. But if there was debris around the star and it's orbiting the star, then we should see that dramatic dimming again within certainly less than a year, and we haven't. So don't know what's going on there. Or it could be because this thing is swelling out, it sucked in a planet. And as it sucked in a planet, we happen to have the star rotating in front of us, and the damaged spot, the bruise on the star, where it sucked in some maybe, Jupiter or Neptune sized planet and obliterated it, that spot got absorbed by the star as it grew out. And so you get a one-time dimness and then you don't see it again, which that's probable. But you're eventually going to run out of planets to consume. What if it was a binary star system and it consumed its companion star? Well, usually when that sort of thing happens, it doesn't just go quietly. It makes kind of like a jet out of the star. As the additional energy gets consumed, it gets converted from the plasma of this star to the plasma of that star minus a bit. And the minus a bit jets out, and they didn't see that. So the question becomes, what is the exact dimmest such a star gets before going supernova? So when it got dimmer, they were already, it's going to go nova, and then it didn't. Well, how dim does it get before it goes nova? Don't know. So there's the first unknown. Okay, what is the brightness that it gets as it's going on into nova? So if it's going to nova, that's really bright. So if it starts getting all of a sudden not dimmer, but brighter, is there something else going on, like consuming another star or a planet or something, that would make it temporarily an order of magnitude brighter? Like instead of a 0, maybe it goes to like a negative 0.5 or something, gets really bright, and then goes back to normal dimness. We don't know. So given that it's a variable, and given that its period of variability is not static, and given that it's munching on stuff, all of these brightness and dimness red flags aren't really that you can't take them to the bank kind of thing. So what is the evidence for the supernova process? It's a combination of theory and simulation, but it seems to make sense. One of the kits we used to do from the NASA Night Sky Network was Supernova. I think it was more about the kids having fun with bouncy balls. But as the star runs out of simple elements to fuse, like hydrogen, helium, it starts fusing heavier elements, calciums and neons and calciums and carbons. And when it gets to iron, it takes as much energy to fuse iron as you're going to get out of it. So the net product is no additional energy. You went and spent a lot of energy to fuse the iron, but you're not going to get any more energy out of it, which means that the gravitational pressure on the exterior of the star wins, and the star gets crushed inward. This is part of the theory in the simulations in computers. It gets crushed inward, and it gets to a certain level of compression, and it can't go any further, but the accelerated force of the external part collapsing in due to gravity hits this minimum diameter and reverbs. It bounces back out, and that's actually the supernova explosion. When we get later in the presentation, we'll talk about neutrinos, and the neutrinos don't have such an issue. They can collapse down, and they'll be the first energy back out of the star before all the heavier stuff. So the theory is predominantly based upon observations of supernova occurring in other galaxies. We don't get to see them before they go nova because they're just in the disk of some distant galaxy where you can't spot the individual stars. We get to see it as it dramatically brightens to be a brighter star than any other star in that galaxy. So we see it not before it goes supernova, not as it's going supernova, but as it's already expanding out from having supernova, and you see the star. Great, now we see a supernova in a distant galaxy. And at the point where it dims back down, it can no longer be seen in the disk of that galaxy. It just like, it disappears. Now, if the star becomes a neutron star or a black hole, it would be so dim that we couldn't see it from Earth anyway. So what evidence do we have of supernovas within the Milky Way? Let's just say the last one was in 1604 and didn't have a lot of technology back then. So not a lot of high-tech observing going on. Made a note, saw a new bright star tonight, was brighter than these other stars, so, and it only lasted for a few weeks. So yeah, that's evidence of a supernova behavior. Now, when the supernova Betelgeuse occurs, whenever that's going to happen, we'll want to, now that we have all this technology, observe it, record it in all possible wavelengths from radio, infrared, visible, ultraviolet, X-ray, gamma, and neutrinos. So all hands on deck. But how do we know when it's going to occur if we don't know when it's going to occur? So we have an imprecise predictability. The only recorded supernova observations we have are after the supernova has already started. We've never observed them before or during the transition to a supernova. We have no evidence of that, only after it's well into it and it gets bright enough for us to see it in a distant galaxy. This is why astronomers around the planet, and that's bubbled out into social media, Betelgeuse, got to keep an eye on it because you need to catch it right as it's going nova. No, you want continuous observation so that you have stability until it's no longer stable, even before it gets brighter, to record that. So now, given that data, and you watch it all the way out until it becomes its brightest and then gets dimmer and disappears into being either a neutron star or a black hole, you can now validate all of your theory and your computer simulations with observations. This is how the scientific method works. So how often do supernovas occur in a galaxy? Well, seeing as how the last one we saw was in the 1600s, they don't occur all that frequently within our galaxy. But what they did was say, okay, if the blue-white supergiants and the red supergiants are the only things that go supernova or hypernova, how many of those kind of stars are there? And from the spectral analysis of those stars, we can judge the metallicity, or how much hydrogen, helium they have left. So we can judge their age. So if we take the star type, the age, the brightness, and we put that kind of on a plot, we can judge how old the stars are in a given population. So if we go back to when the Milky Way only had, let's say, a few billion stars in it, and we judge that off of this chart, and we say, well, that ought to tell us about how many supernovas per period of time we should see. Well, the estimate is higher than the actual observation. And I think that's because with the Gaia wide field observing, we found out, gee, there's a lot more stars in the Milky Way than we originally thought. And the vast majority of them are not supergiants, either blue or red. They're actually orange and red dwarfs. So the balance of, have we got a lot that are going to blow up, or have we got a lot that are going to be stable for a very, very, very long time? Looks like we got the stable ones. And since we have no direct data equal to this star chart on population and type densities for other galaxies, because we can't see all the individual stars in the other galaxies, they made the presumption that, well, everything's like the Milky Way because that's the only thing we have observations on. So they made the presumption that the novas you're seeing in other galaxies are based upon the identical populations of the Milky Way. So if you have a different shape of galaxy, or a galaxy that's merged with other galaxies, and you can see that, and you're still using the population chart from Milky Way, you could be way off. That other galaxy could have far more frequent supernovas. So if you're judging supernova frequency based upon how often you see them elsewhere, with a chart that maps the Milky Way, the dots don't connect, so to speak. So when is it going to happen? Don't know. But we know what's going to come first, because we know this from looking at the sun and other stars, and from supernovas that have happened in other galaxies. Neutrinos. These are near massless particles that don't really interact with a lot of anything else. So when the star starts to crush in and the energy starts to come back out, they literally have no obstacle to leaving the star. So they're going to leave the star hours to days before we start to see the star in other wavelengths. So when our couple of neutrino detectors on the planet, not a lot of them, a couple of them, when our neutrinos detectors suddenly go off with a big spike, and then you judge that by what part of the sky it came from. So it can't be just one detector. You've got to use a couple of detectors to see what angle the neutrinos came in from. And you find out it's either in the Orion constellation or it's in that general direction of the sky. Send out the word, have everybody, every telescope on the ground, out in space, every different wavelength, every different instrument. Take a look at Betelgeuse for at least several days to a week, because we just saw the neutrino forebearer signal and it should go supernova real soon. So when you see that in social media and on the news channels and stuff, we've just detected massive neutrinos from Betelgeuse. Yeah, now you can say any day now. Now, for people to say, why don't we train the James Webb Space Telescope on Betelgeuse right now? Surely we could see much finer detail and see this live roiling going on. Problem is, the JWST is an extremely sensitive telescope, and it only looks in infrared, but it's extremely sensitive. And even Betelgeuse, as it stands right now, would overpower the detectors. It would just be white, so to speak. So not a good telescope for it. Neither would be Gaia, because Gaia is also a wide field, very dark sensitive telescope. Hubble, there's a telescope you can use to look at Betelgeuse, but the neutrinos come first. So what is this roiling I'm talking about? Well, they haven't come up with a conclusion as to, is the roiling just kind of normal for a star like this? Because it's a red supergiant and it's growing. Is it normal for them to do this? Or is this kind of a timeline step towards supernova? Or is it something else? So as I said, they've used radio telescope arrays to look at the surface of the star in radio wavelengths, and they can see it kind of roiling, like bubbling in spherical shape. So they created computer simulations to try and reproduce why it would be roiling. And they did that. And there was no clear indication that it was going to be because the supernova is imminent. So if you see one of these colorful orange and red, kind of looks like spherical bubbling lava, that's not the image. That's the computer simulation. The image itself looks pretty much like a close-up picture of a star. It's a blob of different colors. And over time, the colors shift. So don't be confused by the high-resolution videos or computer graphics. And when you see an image that looks better, realize it's probably false colored, and that's not what it looks like in visual. So in the back of a lot of people's minds is, yeah, but when this thing goes boom, what about us? Is there any danger to Earth if this thing goes supernova? And as I said, Betelgeuse is roughly 500 light years from Earth. 500 light years at about 6 trillion miles per light year is 3,000 trillion miles. It's in our galaxy, but it's not close by. If it goes supernova, maybe in the next 100 years or so, it's already done that. The light just hasn't gotten to us yet because it's that far away. Now, over the vast distance between us and Betelgeuse, that explosion is either spherical or donut shaped, depending upon how fast the star is rotating. If it's rotating slowly enough, that sphere will have to spread out, 360 by 360, and it's going to lose a lot of energy as it crosses the 500 light years. So I'm not worried about it. If it's rotating fast and it becomes donut shaped and the plane of rotation is not aimed towards Earth, it's like above or below, I'm also not worried about it. If it's directly in the plane of the solar system when it goes off and it's donut shaped, I'll think about it, because that would direct more energy towards us. How much more, we'll never know. When it goes supernova, it might actually be naked eye or telescope visible in the daytime for a few days to a month, that will make people wake up as, what's that UFO? It came out of nowhere. It's always in the same part of the sky. It goes across the sky as time changes. And what's that all about? Oh, people interested in science. Cool. Whether it'll become brighter than the full moon in daytime is unknown. It will not become as bright as the sun in the sky. So we won't have a second star in the sky from here on out, as 2010 might suggest. It'll definitely be naked eye visible in the nighttime for a much longer period of time. And we'll have a lovely diffuse nebula where there used to be a star called Betelgeuse in the constellation Orion. How would you look at this thing? Well, you can look at it right now, except where we live in South Florida, the Orion constellation is not conveniently up all night long. It's farther along because it's a wintertime constellation. So if it goes boom, while we can't see it except in the daytime, we'll only get to see the supernova in the daytime from South Florida. But other places on the planet, we'll get to see it differently, and Hubble Space Telescope will get to see it differently. But it's another one of those, if you don't know exactly when it's going to occur, how would you schedule a public observing event? Nobody wants to hear that in government. It's like, you're telling me you want to have this event, you don't know how many people are going to show up, and you don't know when it's going to happen. I can't help you. But the supernova remnant will be around for thousands of years. So the diffuse nebula where Betelgeuse used to be will be a change in the sky from there going forward. The maximum brightness might be, if it's a few days, probably won't be able to schedule an event. If it's the better part of a month, we can probably quick turn around an event and observe it, maybe at night, maybe in the daytime. That ought to be interesting. So after the supernova is gone, you'll be able to see what's left, maybe naked eye, maybe only through binoculars or a telescope, for years to come. Plenty of time to plan for that. There is a supernova remnant in the Milky Way that's been around for as long as any of us have been alive, and that is the Crab Nebula. It is a radio pulsar about 5,000 plus light years away. It is magnitude 8.4, so it's not naked eye visible, but it is easily visible in optical or radio telescopes. So knowing that we had a nova and a potential supernova in the not too distant future, I picked up a 100 millimeter wide field Newtonian refractor telescope and an 8 megapixel IP video camera. And I've got a little bit of software to write. If you remember, I used to take a telescope with a IP camera out to public events where people could, on their mobile phone, connect to the telescope camera and get a current picture from it instead of trying to put their phone up to the eyepiece. I'll just take that software, rework it a little bit for this telescope and this camera, and then if we do a public observing event of the supernova of Betelgeuse, then I'll bring that along. That'll be fun. So in conclusion, yes, there is a star called Betelgeuse. It is a red supergiant star. It will eventually supernova. The question is when. The behavior of giant red stars at end of life has never been directly observed, not directly from start through transition. The only ones we have on a regular basis are outside the Milky Way. And even those we don't have before, upon onset, and then after. We only have as it's already started and then after. What people are saying as to how stars behave at their end of life is what we know from calculations and predictions. We have graphical computer simulations, and many people might consider, oh, I saw the picture on the internet. That's like from observations of like supernovas. Nope, that's a computer simulation. That's not actually an observation. So whenever you see it, if it looks too pretty, it may not be anything other than a computer simulation, which may mean, given that we don't have any observations to back it up that are direct, that may not be what happens. So if the supernova Betelgeuse happens in a manner befitting the limited patience of humans, meaning hopefully sometime this year, it will be spectacular. I heard this week that the supernova of T Corona Borealis, not supernova, the nova of T Corona Borealis has been moved from April to September to now September to November. If you remember in the presentation, I said, the numbers don't look right. I think this is going to be about a year and a half to 2 years out from now, because as you nova and you recur your nova, you're giving up energy. So it takes longer to collect more accretion disk to make it go nova again. So the nova periods should be lengthening, and they're looking at it shortening. And I just don't see it doing that, but that's just my opinion. So when it happens, will the population of Earth survive? Presumably so. If not, we're a single planet species. Don't worry about it. There's nothing we can do. And I did update it. Now says I have 9 optical telescopes. It used to say 8. And we've got the usual links. Betelgeuse, the Orion constellation it's in, variable stars, what those are all about, what supernovas are about, the history of supernova observations from early Chinese observations where, yeah, we think that was a nova. We're not really sure. And then I've got a bunch of links to NASA JPL Night Sky Network resources, the Supernova Toolkit, manual for it, and there's a really nice predictive star chart of where we think the next novas are going to happen and supernovas are going to happen. And yep, Betelgeuse is listed. And then for background information, what's a nebula? The actual Betelgeuse Roiling under radio astronomy imaging that I saw. What the Crab Nebula supernova remnant's all about. The pulsar at the core of that neutron star. What neutrino detectors we have. And specifically, the one down in Antarctica, buried in the ice, called the IceCube. And then that star chart that showed the population, different types of stars in the Milky Way. There's a nice explanatory video that the IEEE provides access to for free, so you can watch that video. It's only, I think, 4 or 5 minutes long. And thanks for watching.
Well, thank you. Love it.
Comments, questions, predictions?
That'll be good.
Well, what generation star are Betelgeuse and our sun?
Our sun is is older than Betelgeuse by millions and millions of years. Betelgeuse is quite newer. I think I said it was 10 million years old, whereas our star is about 4 billion years old and has maybe another 4 or 5 billion left.
It's a baby compared.
Yeah, I understood that. I'm wondering about the generation, though, because you had talked before in other ones after the Big Bang, how there were different generations of stars, and
yes.
I'm just wondering, the thought behind it is, if the star is really big and only the very fact that you say it's like 10 million years old, I mean, that's not even a toddler, right? That's right. A baby. That if stars that are really huge collapse more quickly, then you wouldn't think there would be many of them around. So, and I guess from the composition of it.
That's what the Gaia survey is finding. The Gaia survey is finding the total population of stars in the Milky Way. There are a lot more of them that are orange and red dwarf stars than blue supergiants or red supergiants. The difference between the blue and the red is literally the temperature of them, not so much the chemistry as the temperature. The way you detect how old or what generation a star is through its metallicity. And by metal, I don't mean like iron and aluminum kind of thing. I mean the metallic elements, which includes things like helium. Helium is a metallic element. And strangely enough, if you compress it enough under low enough temperatures, even hydrogen has been known to conduct. So it's not officially a metallic element, but if you compress it enough, like at the cores of Saturn and Jupiter, then you get magnetic fields, so electrically conductive. The element that I remember being used to judge the generation of our star is an isotope of lithium called lithium-8. And if your star has lithium-8 in abundance, then your earlier generation. And if you have less lithium-8 in your spectra, then you're the next generation out from there. So I haven't looked at the spectra for Betelgeuse, but given that they've already identified its age as being far younger than our sun, the question would be, if our sun was created so much farther back in time compared to Betelgeuse, what things in the area of Betelgeuse would have led to its creation, given that it only happened 10 million years ago. Remember that space is three-dimensional, and when you think about, must have spun out of the Orion Nebula. The Orion constellation is about 1,000 light years deep in 3D. So the Orion Nebula is not actually anywhere near Betelgeuse. Angular separation in the sky from our perspective on Earth, it is, but in the depth of three-dimensional space, it isn't. So what was the source for Betelgeuse? I don't know, the Flame Nebula, which is angular separation again in that part of the sky. Maybe it came out of there. Maybe it came out of something else. And it was such a small nebula that when Betelgeuse formed, it sucked it all in and blew out all the rest. So we don't see the nursery from whence it came. But I don't see questions like that being asked elsewhere. They only want to know the Punch and Judy story of, when is it going to blow up? What's it going to look like? How long is it going to last? Can I see it in the daytime? So, but I always like to get into the minutia and ask the questions that other people are just not, I connect dots where other people can't see the dots. Okay. Any other comments or questions? If not, I'll stop recording.